Next is a novel snake robot for nose, presented by Dr. Michael Awad.
Good afternoon. Thank you to SAGES and to the panel chairs for the opportunity to present to you this afternoon. I'd also like to acknowledge our co-authors, as this was a multidisciplinary study. Dr. Sham Thacker, a gastroenterologist from Drexel University, as well as Dr. Howie Chosit, a roboticist from Carnegie Mellon University, who are both in the audience today. In looking at the evolution of minimally invasive surgery, we are reaching a time where that is the ability to do complex laparoscopy, single incision surgery, as well as natural orifice surgery has been limited by the advancements in technology. And if we look at conventional approaches to these various techniques, laparoscopy, its ability to perform complex laparoscopy has been limited by the rigidity of traditional laparoscopic instruments. Flexible endoscopy also has hit a wall as far as the lack of dexterity. And as far as current robotic platforms, it's limited by its mobility, as we heard in the robotics panel this morning, the size of the device as well as its limitation to single quadrant surgery. So in order to break these barriers and allow surgeons to achieve this holy grail of performing complex laparoscopy, single incision, and natural orifice surgery, I do believe that flexible robotic platform will be the solution. And towards this, there's been a number of snake robots that have been developed. What's shown here, developed at Carnegie Mellon University. And these were initially designed for use in search and rescue operations for victims in trapped buildings, as well as in archaeologic digs as well, and have recently been adapted for use in the medical field. This is an example of some of these snake robots in use in industry. And you can see that they're basically modular units that can do a number of things. Some things you may not want them to do. Don't worry, it does stop. But basically, they're multifaceted machines that have the capability to perform a number of maneuvers, the rolling, crawling maneuvers. This is kind of as it be imagined in a search and rescue type operation. There's a camera at the end that's used to get through tight spaces and visualize in nooks and crannies. This is a climbing maneuver that the robot is able to perform, as well as swimming functionality, something you hope not to find when you're swimming in a lake. The version of this robot that was adapted for surgical use is known as the MICS, or minimally invasive cardiac surgery robot. It was initially developed for performing cardiac surgical applications. This is a teleoperated probe, basically, that's controlled by a joystick. So in distinction to current endoscopic platforms in which the dual dial configuration is employed, these are controlled in a simple fashion with a joystick. It's comprised of a series of links. It's meant to drive through basically any luminal space and can assume the shape of its surroundings. Furthermore, the links can be made of any material and are meant to be either disposable or reusable. The current design employs a 12 millimeter outer diameter and thus has potential for endoluminal applications as well. This particular version of the robot has 3 working channels. They're each 3.4 millimeters in diameter, typically used for 2 flexible instruments as well as a fiber optic endoscope. This is a picture of the version of the snake robot adapted for surgery, the MICS robot, and you can see the multiple segments that is comprised of. Virtually any number of segments can be added to this, allowing for tens, if not hundreds, of degrees of freedom. This is a close-up of the same robot with the 3 lumens at the tip. This is an example of the housing for the robot. You can see the one version of the joystick in the back there that controls the operation of the robot. In this particular study, it's just a proof of concept. We did a distal pancreatectomy in a porcine model. A transrectal NOTES approach was used with an overtube. A posterior rectotomy was created with a balloon dissection in a standard fashion using a conventional endoscope. Two abdominal ports were also utilized during the procedure. One was a viewing laparoscope and the other was a fixed retractor. As far as instrumentation that was used, an endoscopic biopsy forceps as well as needle knife cautery and snare were employed. And this is the video of the porcine distal pancreatectomy. This is the robot coming through the overtube is shown there. That is the pancreas of the pig seen in the center of the field. This is a standard endoscopic biopsy forceps that's used to manipulate and grasp the tail of the pancreas. This is a needle knife cautery that's used to do the electrode dissection. And the robot can be used with some dexterity to control the angulation and extent of the dissection. Here the dissection is being completed with the specimen at the top of the screen. At the completion of the procedure, the specimen is retrieved with the snake robot through the overtube. As shown here. So the total procedure took 118 minutes, just under 2 hours. No overt complications were noted. Also, as an additional note, all 4 quadrants of the abdomen of the animal were viewable from this approach, which is perhaps an important advancement over current robotic technology. As far as future directions, the optics could definitely be enhanced. We're also working on the instrumentation actually being robotically controlled instead of using current flexible endoscopic technology, and looking at approaches through transgastric or transabdominal single port approaches as well. Thank you.
Questions from the floor? I was, it's a very impressive technology, but I guess ultimately the application here looked to me very similar to what you would do with perhaps a standard endoscope. Is there the ability to use, 2 separate snake robots as 2 separate arms and give a whole different dimension to the dexterity?
So that's a great question, and what we didn't show was the actual ability of the robot to snake through different cavities in the body, which perhaps is an advantage over the current endoscopic technology. But as you say, the ability to control each of the instruments robotically would be a tremendous advancement. What another option would require is slightly larger outer diameter of the robot, but we could then put 2 smaller robots within that sheath to achieve that purpose.
Thank you very much.
Thank you.